In the previous lecture, we discussed about the meaning of polarization, types of polarization, and three methods of polarization, namely Weiergate polarization, polarization by reflection, and polarization by dichroism. In this lecture, we shall discuss the polarization by birefringence or by double refraction. In this, the phase retardation plates and construction of Nicol prism will be discussed. Now the next method of polarization is the polarization by double refraction. It is also called anomalous refraction or birefringence. In nature, there are some materials which show double images of objects when they are seen through these materials. These materials are known as birefringent materials, and this phenomena is known as birefringence. It happens because when an unpolarized light ray enters in birefringent material, it suffers splitting into two rays. One of those rays obeys Snell's law, while the other does not. The first one is called the ordinary ray or O ray, and the second is known as extraordinary ray or E ray. The most important quality of these rays is that these rays are separately linearly polarized. The plane of vibrations of these rays are perpendicular to each other. But by merely placing birefringent crystal in path of unpolarized light cannot produce polarized light. It is because when O ray and E ray emerge from the crystal, they are no more O ray or E ray. They are ordinary ray with velocity c in air. And since they travel along the same direction, the resultant ray is again unpolarized. So the question is how to use birefringent materials to produce polarized light. To know the answer, let us discuss few more and important properties of ordinary ray and extraordinary ray. The birefringent crystal is isotropic for ordinary ray. The meaning of this is the ordinary ray has the velocity in this crystal same in all the directions, and it is given by VO. But these crystals are anisotropic for extraordinary ray. Means the velocity of extraordinary ray in these crystals is different in different direction, and it is given by VE, where NE is a constant for extraordinary ray in that material. For theta equal to 0 degree or 180 degree, VE is equal to VO. It means there is one direction in which VO and VE are the same, and the direction is known as optic axis of that crystal. When unpolarized light enters the birefringent crystal along optic axis, it does not split it into two rays. If ordinary ray starts traveling from a point in these crystal, in a unit time it reaches a periphery of a circle as its velocity in all the directions is the same. While if extraordinary ray starts traveling from the same point in these crystals, in a unit time it reaches the periphery of an ellipse due to different velocities in different directions. So O ray and E ray are represented by circle and ellipse respectively. In some birefringent crystals, VO is greater than VE, and in others, VO is less than VE. The first one are known as positive crystals, and the example of one positive crystal is quartz, and the other one are known as negative crystals like calcite. In positive crystals, ellipse is inside the circle, while in negative crystals, the circle is inside the ellipse. In both types of the crystals, the ellipse and circle touch each other along the optic axis. These are few more examples of positive and negative crystals. If the positive and negative crystals are cut so that the optic axis lies on its surface, then the light which enters the crystal will definitely get splitted into ordinary ray and extraordinary ray. It is to be noted that the plane of vibrations in ordinary ray and extraordinary ray are perpendicular and parallel respectively to the optic axis. Now, the fast moving ray is ordinary ray in positive crystals and extraordinary ray in negative crystals. So, there will generate a phase difference between ordinary ray and extraordinary ray on emergence from the plate depending upon the thickness of the plate. Therefore, the plate of positive or negative crystal introduce a phase difference between two orthogonal polarized rays, ordinary ray and extraordinary ray. And therefore, these plates are known as phase retardation plates. If introduced phase difference is pi by 2 or the path difference is lambda by 4, then this plate is known as quarter wave plate. And if the path difference is lambda by 2, then the plate is known as half wave plate. And if the path difference is lambda, then this plate is known as full wave plate. As we have already studied that the two 90-degree phase shifted orthogonal linearly polarized light rays superpose to give circularly polarized light ray or elliptically polarized light ray. Therefore, a quarter wave plate can be used to produce circular or elliptical polarization. The thickness of phase retardation plates can be found by calculating path difference between the rays O ray and E ray when they emerge from the plate. So this path difference is the extra time taken by a slow moving wave to travel the thickness T of the plate in the birefringent crystal multiplied by the speed of light outside the crystal. Then this is the time taken by ordinary light ray to travel through the plate, and this is the time taken by extraordinary light ray. So the path difference is the time difference multiplied by C. So C divided by VO is mu O and C divided by VE is mu E. These are the refractive index of this plate for ordinary ray and extraordinary ray. For a full wave plate, the path difference is lambda. If we equate this lambda with this, we get the thickness of full wave plate is equal to lambda upon difference between the refractive indices. For half wave plate, this path difference is lambda by 2, and so T half is equal to lambda upon twice the difference between refractive indices. And for quarter wave plate, path difference is lambda by 4, so T quarter is equal to lambda upon 4 difference between refractive indices. So this is a phase retarder plate, which is quarter wave plate, and this is a polarizer, and this is the unpolarized light ray. Now this is a polarized light ray with its plane of vibration inclined at 45 degree with the optic axis of the quarter wave plate. Then the emerging light ray is the circularly polarized light ray. So a quarter wave plate can be used to convert a linearly polar light into a circularly polar light or an elliptically polar light. Before going to the question how to polarize an unpolarized light, we talk little more about the calcite crystal. It is a negative birefringent material, means the velocity of ordinary light ray is less than that of extraordinary light ray in this crystal. So the crystal structure of calcite is rhombohedron. This is the crystal structure. And the 6 phases of this rhombohedron are parallelograms, each having the angle of 102 degree and 78 degree. There are two opposite corners A and B in this crystal where the three obtuse angles of 102 degree meet. These corners are known as blunt corners. At the rest of 6 corners, there is only one obtuse angle and two acute angles. A line passing through these blunt corners is known as the optic axis of the crystal. So any plane which contains the optic axis and it is perpendicular to any of two opposite phases is called the principal section. In the principal section of any calcite crystal, the angles are equal to 71 degree and 109 degree. So if this is an optic axis, then we can draw three planes which are perpendicular to any of two planes in this crystal, and that contains this optic axis also, like this or like this or like this. So these three can be the principal section of the calcite. So here this is the principal section. When an unpolar light incidents on this principal section, then it gets split into extraordinary light ray and ordinary light ray. So this ordinary light ray has the vibrations perpendicular to this plane, and this extraordinary light ray has the vibrations of electric field in this plane. So these are the angle of reflection for these two splitted rays. So to make a polarizer by calcite crystal, Nicole constructed a prism. In this, he took a principal section of calcite with its length 3 times than that of the width, and then he ground this face and this face so that this angle reduced to 68 degree from 71 degree, and this angle increased to 112 degree from 109 degree, and this is the optic axis. Now he cut this crystal in this diagonal direction, and he polished it optically, and then again joined it using a transparent medium Canada balsam. This Canada balsam is not birefringent material, but calcite is. The refractive index of ordinary ray and extraordinary ray in this calcite are this and this, but the refractive index of Canada balsam is the same for extraordinary ray and ordinary ray. This arrangement is called Nicole prism, and it is used to polarize the light. But to do so, we have to separate the E ray and O ray. For this, we use the help of total internal reflection, and it is described as follows. As the Canada balsam is rarer medium for ordinary ray, it may suffer total internal reflection if the light incident at the left end of the Nicole prism at such an angle that the ordinary light ray incidents on the calcite to Canada balsam interface here at angle greater than the critical angle. This critical angle is calculated to be 69 degree in this case for ordinary light ray. At this angle of incidence for ordinary ray at Canada balsam interface, the ordinary ray suffers total internal reflection, but the extraordinary ray passes through the prism, because for this Canada balsam is denser medium and so it cannot suffer TIR. In this way, we get a polarized light at the other side of the Nicole prism. It can be calculated that for this to be happened, the angle of incidence I for incoming unpolarized light at the left hand face must be less than or equal to 36 degree, or the maximum angle of incident light with the horizontal must be 14 degree.